All right. Welcome, everybody. My name is Christian Schaffner. I have the honor of chairing the last session of this year's QCrypt. We're going to have 3 talks. The first one is an invited talk by Andreas Huelsing, and he's an expert in post-quantum cryptography from the Technical University in Eindhoven. Andreas.
So thanks for the introduction, and thanks for having me. I will talk about post-quantum cryptography. And while going through my slides, I recognized that this is a talk about problems, essentially only about problems. So it starts with the problem. The point I want to make is post-quantum cryptography is kind of a problem-driven field. So there is a problem, and we wanted to solve this, and that's where it comes from. And I want to make the statement because sometimes, especially at this conference, there seems to be like people have the impression that there's a competition between post-quantum and QKD. I honestly do not see this because the problems are different. And I want to present you the problem that post-quantum actually solves. So the problem starts with something called public key cryptography. So public key cryptography means, in contrast to secret key cryptography, where 2 parties share the same secret key, every party has a key pair consisting of a public and a private key. I think most in the room probably are familiar with this concept. So you use the secret key for your secret operations, and the public key you hand out to the public. And so the 2 main primitives in this area are digital signatures. On the one hand, they give you a proof of authorship and provide authenticity and non-repudiation. And what's important here is this is transferable. So it's not like a Mac where you have this within a session but cannot prove to a third party that something is authentic. In this case, you can really prove to a judge that someone signed this. The second thing is public key encryption, key exchange, key encapsulation mechanisms. They are, for the matter of this talk, essentially all the same. There are differences, but essentially, they allow you to establish a commonly known secret key without having communicated before. So without having shared a secret beforehand. And so that way they provide secrecy and also allow you then to protect symmetric ongoing communication. So the most important applications in this context are code signing. On the one hand, where you use digital signatures, so software updates, software distribution, and mobile code. I just remembered, for software distribution, I actually bought my first Linux. I still had to pay because I bought a box with the CDs in there. So that was the way previously software was distributed. If we don't want to fall back to this, we actually need digital signatures. Because otherwise, if you download your software package, you cannot guarantee that this is authentic without digital signatures. On the other hand, we've got communication security. So there we use digital signatures to actually guarantee the authenticity of a public key for one of the public key encryption and similar schemes, which are then used to establish a common secret key. So this is used in all your favorite security protocols like TLS, SSH, IPsec, which run below e-commerce applications, online banking, e-government applications, and so on, and also private online communication. Just to give an example, like if you meet a nice person and exchange phone numbers at some point, immediately asking for exchanging encryption keys might go a bit far. I mean, the person might get the wrong impression. So to go further, the canonical example for this connection security is, for example, Alice wants to throw a tea party and doesn't have tea at home, so she goes to the internet, looks for some tea shop, and finds some nice tea shop, which she obviously didn't know before that she will ever want to visit this tea shop and wants to buy something from that shop. So she has to transfer her credit card data at some point. And so she wants a secure connection. So what happens is Alice initiates the connection, then the tea shop will send its public key and a certificate, which is essentially a signature on the statement, this public key belongs to this tea shop by some trusted third party. And then the 2 start establishing a shared secret using public key cryptography. And in the end, the channel is then secured using secret key cryptography. So how do we build public key cryptography? We start with some computationally hard problems. So actually you can prove it is impossible to build public key cryptography in an information theoretically secure way. That's just because the key generation function always gives you a one-way function. So an unbounded adversary can always go from the public key to the randomness used by the key generation mechanism and then obtain the secret key. So we need some hard problem in there. And the problems we use so far are RSA, discrete logarithm, all these number theoretic problems. And then from these, we build public key cryptographic schemes. We typically do this in a way that we can prove that if someone can break the scheme, that person can also break or solve the hard problem. Okay? And so the problem actually starts at this point, namely, as all of you know, as soon as we have large, so few thousand logical qubit quantum computers, we can actually efficiently solve these previously used problems. So then factoring and discrete log are not computationally hard anymore. So all the previously used public key schemes are broken, and we don't have key exchange, key encapsulation, public key encryption, and digital signatures anymore. However, the symmetric part actually remains secure, as far as we know. So there are actually bounds, at least for generic attacks, that say you cannot do better with the quantum computer than just square root speed up. So that looks good. And this is a problem that QKD actually cannot solve, because that's a public key scenario where you really need a computational assumption. I'm not saying that quantum cryptography cannot solve it, but QKD as a key growing mechanism cannot solve this. But post-quantum cryptography can, because it was especially designed to solve this issue, like replacing today's public key cryptography. And so that's essentially the context of early post-quantum cryptography. So that was pretty much limited to cryptography based on problems which are conjectured to be hard even for quantum computers. And I will go into these problems, so I will skip over this now. The more modern approach goes actually beyond this and generally considers a setting where we have users that use cryptography on conventional devices and face quantum adversaries. So this then suddenly includes topics like how do we argue security, are our security models still sound? For example, Dominic had this work on the binding property of commitments, which does not really, the classical definition doesn't work anymore in the post-quantum setting. And also we actually want to know what is the complexity of quantum attacks. So the early days, it was more like, okay, there are no quantum attacks, and now we estimate parameters using classical attacks and wait for quantum computers to come to actually select quantum secure parameters. And so maybe I have to emphasize this again. So this is a computational complexity approach. So we cannot build public key cryptography without any hardness assumption, which means that we actually need cryptanalysis to determine the complexity of solving these problems or then breaking the systems. So we cannot select parameters in a different way. There's actually no way known to prove that these problems are at least as hard as X. If you would do this, then you probably would pretty much get a proof that P is unequal to NP. So there's not much hope for this. So what are these conjectured quantum hard problems? We've got solving multivariate quadratic equations, the MQ problem, which gives you multivariate cryptography, the syndrome decoding problem, and variants that give you code-based cryptography, the shortest and the closest vector problem, which gives you lattice-based cryptography, then breaking the security of symmetric primitives, so breaking the SHA hash functions, AES, Ketchak. These are all kind of dedicated problems which lead to hash-based signatures and, of course, symmetric cryptography as such. And then there's a relatively new problem, which is finding isogenies between super singular elliptic curves of the same number of points, which leads to something called SIDH. That's pretty new. I think that might be interesting also to look at this with quantum algorithms, but I will brush over this in this talk. To give you some context, we heard yesterday in the industry session, there's the ongoing NIST competition, or not competition. So the idea is to select post-quantum schemes for standardization. And to give you an idea, so Dustin Modi said on the first NIST post-quantum security conference, like the conference where they officially kicked off the competition, we see our role as managing a process of achieving community consensus in a transparent and timely manner. So the main thing I want to say here is that actually the community is analyzing these schemes. The community is proposing schemes, and then also the community is analyzing schemes, so everyone is invited to actually participate in this. Especially NIST will not do a lot of analysis themselves because they don't have the capacities, as they say. And so the status of this competition so far is end of last year, the submissions were collected, and around Christmas, NIST actually published the complete and proper proposals. So these were just the proposals that fulfilled the official requirements, like handing in all documentation needed and not analyzed to any in any regard. And this started round 1 out of 2 or 3 rounds, and NIST is not clear about this. And what now happens is actually cryptanalysis of these schemes starts, and then also the efficiency will be analyzed later on. And the goal is to have draft standards in 4 to 6 years. And the submissions factor into the different problem areas as follows. So most are in the area of lattice-based cryptography. Then we've got code-based on second. Actually, multivariate is third. Hash-based has just 3 signature schemes. And then we've got all the funny stuff. So there's a braid group proposal. I would say this is as dead as possible. But somehow the company that submitted it is still animating it and claiming it's still moving. So yeah, we've got a super singular elliptic curve algorithm. So that's the reason why I will not go into details there, because we only got 1 submission. We've got 1 satirical submission, which actually proposes post-quantum RSA. And is using that still, even if we have quantum computers, there's a gap between the attack and the actual honest execution time. And then there are 4 new other submissions, of which 3 are actually broken. 2 of them also withdrew. And 1 scheme which is by a lot of popular cryptographers. It might also, a similar scheme was put into the code-based area. So there it's just, we didn't know what this problem really links to. So the current evaluation results are, if you look at the submissions, you see this is different from a symmetric competition. So you don't pull a new public key encryption scheme out of your head within a year. Like this needs a lot of analysis, and these submissions generally follow a few previously known theoretic constructions, and they actually differ in how you implement the fine details. So there's a lot of, there will probably be a lot of merging at some point because a lot of submissions are pretty similar. And so far there were 11 attacks on 10 schemes, but these were no big surprise attacks. It was not that anyone could come up with an efficient solution to one of the underlying hard problems, but the attacks either break those schemes which are fundamentally new, so not really relying on established problems, or they actually exploit these implementation decisions. So some people just selected parameters far too aggressively, or some people actually built a hash function, a scheme that we broke, that would compress so far that it's kind of trivial to find a pre-image, which they just didn't recognize because they described the hash function in a strange way. So these are like the things that happen when you rush a submission, and then but I think these are sorted out, and so now we are at the point where we actually have to go to analyze the underlying problems. And so what are these computational problems? The first thing I want to go over is the MQ problem. So the MQ problem says you're given a set of m polynomials in n, in n variables of degree 2 over fq. And then in the MQ problem, you're given a v in the range of this polynomial system, and you're asked if there exists a solution and in a search version to find the solution, like a variable assignment that actually works for this. And the decisional version of this is NP complete, so that also applies for the search version. And people started building crypto from this already end of the 80s. So far, there were mostly only signatures. There are a few very recent proposals for encryption, but these really still have to be studied. So there it's not even clear if there's a hard link to the MQ problem breaking these, or if you maybe can go around the MQ problem. And so the cryptanalytic tasks here, and this will repeat for the problems in some sense, is on the one hand, of course, we need to know how hard it is to solve a random MQ instance. So that's the point where even if this problem is NP complete or NP hard, it doesn't mean that our problems are hard because we use random instances. So we need average case security. On the other hand, we have to analyze the hardness of solving a special MQ instance. So what happens when people generate signature schemes is they would pick an MQ instance which they can actually easily invert so that they can have a trapdoor and then hide the structure of this instance. And so what you actually have to analyze in many cases is if you can somehow exploit the structure that's added and thereby break the system. So far we've got non-quantum attacks, which are essentially what some people call quantizations of classical algorithms. So they take the best classically known algorithms, essentially throw quantum random walks on it, and get roughly a square root speedup. The next problem is the syndrome decoding problem, and you will see these problems look all a bit similar because they are NP hard. So in this case, you're given a linear code, which is a subspace of fq to the n, and you're given a syndrome S and an error bound B, and then you're asked to find an E of weight less than B such that the parity check matrix, H times this E is S. And essentially what this means is you're asked to find a vector, as these are not working well. So you're asked to find if one vector exists. First, the decisional problem asks, am I in one of these balls that I can decode, or am I somewhere outside? And if I'm inside, then the search version asks you to give you the vector that actually links you to the next code point. So that's kind of decoding, but represented in a different way. And this is known to be NP hard also. For the binary case, this was shown in 78. For the non-binary case, so if Q is unequal to 2, this was shown in 94. And the first proposals for this were more or less at the beginning of public key cryptography. So 78, McAleese proposed an encryption scheme, which is now only known as McAleese encryption scheme, where it uses binary Gupper codes. And until recently, we actually didn't have any practical proposals for signatures, but only practical proposals for key encapsulation or public key encryption. And here the situation is as follows. So either you get really huge keys if you take somewhat random codes, or you use structured codes, like for example QCMDPC codes, which are like the latest proposal in this direction. But then you add structure. And so the cryptanalysis tasks are either looking at solving random syndrome decoding instances, and that's what the non-quantum algorithms do. So they work for random instances, and then again, these are quantizations of classical algorithms. They essentially use quantum random walks to improve the best non-classical algorithms. Or you actually have to look into the hardness of solving the syndrome decoding problem for these structures codes. And for some of the structured codes, like there were earlier proposals, like QCLDPC codes were actually broken. But for the new ones and for GAPA codes, this is actually not known. Okay, now if you want to know, oops, why is this shifted? If you want to know why lattices are so popular, one of the reasons is that you actually have nice graphical representations for the problem. So if you're given a lattice described by a basis, then the shortest vector problem asks you to find the shortest vector in the lattice. Pretty trivial. And this turns out to be hard as soon as your dimension grows significantly above 3. So actually for 2 and 3 you've got efficient algorithms, afterwards this stops. And so here you've got essentially 2 problems and their approximate versions. So SVP is the shortest vector problem where you're asked to find the shortest vector. That's known to be NP hard. We've got an approximate version where you're asked to find just a short vector, and then it depends on the approximation factor, like how short this vector actually has to be to decide if it's NP hard, or if alpha is large enough, you actually can solve this with LLL. And you've got variants of this called the closest vector problem and the approximate closest vector problem, where you're asked to find a closed lattice point to some point in space that you're given. And so here the first proposals come from mid-90s, but this has a bit longer history because you need this, for example, for optimization tasks. So people are looking into these problems already for longer, not from a cryptographic point of view, but really from mathematical points of view. The lattice people always like to say this goes back to Euler, and that might be a bit too far, but this is a well-studied problem. One thing about lattices is that you can actually build signatures and key encapsulation or key exchange. That's one of the reasons why this, or the second reason why it's pretty popular, and you can even build things beyond. But then you've got a similar situation as for codes. So you either get huge keys and or signatures, or you actually have to use somewhat structured lattices. So ID lattices or module lattices, the ID lattices are essentially lattices that you can describe by polynomials. And these have a lot of structure, and if you look at the cryptanalytic tasks, actually for these classes of lattices, I have the feeling it should be somewhat easier to break them because you've got this added structure. And also there, people should look at this, but didn't so far. So far, we've got, again, just this quantization of classical algorithms. There's a paper from 2015 that does this for sieving algorithms. We've seen a poster here which does this for enumeration with pruning. So these, again, just give you this square root speed. Now, the last thing are the hardness of symmetric primitives, especially hash functions. So a hash function is an object that efficiently compresses an arbitrary length string to a fixed length string, and that does this in an efficient way. And then we've got essentially 3 core problems. The first is pre-image resistance, where an adversary is given an image of the function and a function description, then is asked to find an input to the function which actually maps to this image. Collision resistance asks you, given the function description, to output 2 domain elements which are mapped to the same range element. And of course, these 2 have to be different, otherwise it would be trivial. And then second, pre-image resistance is somewhat like a target collision. So you're given a domain element and a function description, and you're asked to find a colliding element for this domain element under this described function. And from this, you can actually build digital signature schemes. So the first proposal was in 1979 by Lampert. And one point here is you can only build signatures, so there's no way to build public key encryption from this. We've got different trade-offs here than for the previous schemes. So here, the decision if you get fast and compact schemes or bigger and slower schemes depends on if you're willing to preserve a state, so if your secret key actually changes over time or not. Like, you don't really change the assumptions that you make in the schemes. We also got the special situation for cryptanalysis, because in this setting, at least for the generic case, so if we look at random function families, we got upper and lower bounds for the attack complexity. So there are bounds that say we cannot find a quantum algorithm that, for example, solves collision finding for an arbitrary hash function more efficiently than that it gets after Q queries the success probability of Q cubed over 2 to the n. So that's a guarantee that we cannot or don't know how to obtain in the other cases. But of course, as soon as you look into dedicated functions, there's no guarantee for this so far. And one research area here is also that people really start to look into the cost of more realistic models. So these bounds are all in the model of the query complexity model. But as soon as you actually take the more realistic cost models for quantum computation, these bounds, of course, get worse. So what's the status on quantum cryptanalysis? So far, I didn't find any quantum algorithms that really improve conventional algorithms by more than a square root factor. So all the algorithms I could find were essentially throwing quantum random walks on the best non-classical algorithms. And this would be a call also to this community to have a look at this, because we need to find if there are better algorithms for the more structured problems especially, if possible, before we standardize those schemes. Would be good. Okay, so to conclude, we really need more of this actual quantum cryptanalysis, and that actually needs to be funded, and there also needs to be people in quantum algorithms that look at this. What I didn't have time to talk about, but which I think is also pretty important, is all these problems that come beyond selecting new cryptographic schemes. So all these discussion points of what are the right models when we're proving security. So as I said, the collapsing property, or currently there's an ongoing discussion about the topic of indifferentiability, and also how do we prove security in these models. So we had Renato giving a talk about this real ideal setting also. In these settings, we often do not even know the quantum complexity for the ideal setting. So then there is no point in proving we are close to the ideal setting, because this still doesn't give us any bounds. If you're interested in this, and due to only half an hour, I, for example, hadn't any time to go into constructions. We had a summer school last year on this topic, where the lectures are online, so you can watch the videos. And there we actually go into the constructions. For example, we've got, I think, 4 hours only on hash-based signatures. And that's the link for the NIST standardization, and that's it from my side. Thanks.
Thank you very much, Andreas. Are there any questions?
This is probably not a very deep question, but I saw the word indifferentiability, which I assume doesn't mean the lack of a derivative in the sense of calculus.
No, but it is actually a very deep question, because describing the indifferentiability framework is the idea is, if I build a construction, if I, for example, build a hash function out of a smaller building block, like a compression function, and want to prove that this hash function behaves like a random function, then I would give oracle access to this hash function. But normally I would also have to give oracle access to this building block to the adversary. And then the indifferentiability notion says how I should actually model this and prove this. And Dominic had a poster in the session where they showed under some conjecture that this notion might not be achievable in many settings. And currently there's a second proposal online which keeps the theory community pretty busy at the moment that says it is possible. Yeah.
I see a question up there.
If I understand you correctly, so you have now 4 to 5 years for the cryptanalysis, but these underlying hard problems, I think they have been studied for a longer time. So in these 4 to 5 years, you're basically studying whether the parameters and the implementations are correct or not breakable simply, right?
Yes, so the problems are not new. Especially the problems as such are studied for quite some time. The constructions are more recent, but there we, in most cases, actually have security reductions that say if you can break the scheme, then you actually can break or can solve this hard problem, which means you only have to analyze the hard problem and not the construction anymore. The main point missing is really an estimate of how costly it is for a quantum computer to solve these problems. So I'm not suggesting that a quantum computer will really get a massive asymptotic speed up, like solve these in polynomial time. That's something that would surprise me. But nevertheless, if you get a factor of 1 million speed up, this means we have to select dimensions of the lattices, for example, in a totally different range than we do now. And so that's something that, of course, is extremely hard to predict because we do not even know how costly a single quantum gate is. I mean, is this the same as a classical gate, or is this, right? That's depends essentially also on the way you implement your qubits or you build your quantum computer. And we don't know which way this will be finally.
Thank you.
See, last question over here. Nino?
Thank you. I got a bit confused when you talked about the bounds for the hash algorithms. You said that for general attacks you have an upper and lower bound, but then you mentioned that for specific implementations it's no longer valid. Do you mean by no longer valid that those bounds are no longer valid and can be above or beyond, or that you don't know where within those bounds?
So these bounds, of course, apply to the hash functions in the sense that the upper bound still applies in the sense that it might not be tight, but we've got, of course, an algorithm that solves this for any hash function, so it also solves it for the specific one. But the lower bound, which says like you need at least these many queries to break the scheme, that only holds for attacks that do not look into the internals of the hash function. So you might have a dedicated attack that only works for, say, SHA-2, that doesn't contradict this lower bound. So if that's better than the lower bound.
All right, let's thank Andreas again.